Propulsion Lab, and we're using GPS vertical land displacements to infer changes in water in the western U.S. as a function of location and a function of time each month from January 2006 to the present. And what we're finding is we're finding that in California's mountains, more water is lost during the drought in the ground, and more water is gained in the ground during heavy precipitation than in the hydrology model. So this is really bringing a new piece of information from a GPS technique to the hydrology models. So on the right-hand side, you're going to see a series of water changes each month. So the month will come up right here, starting January 2006, all the way through October 2017. On the right-hand side, there's going to be water change. The reds are going to show water loss. The blues are going to show water gain. And on the left-hand side, I'm going to have the total water storage in California's mountains as a function of time, estimated from both GPS and from GRACE. So what you're going to see is when in the fall and winter, when the snow goes onto the ground, there's greater mass, so the earth subsides because of the weight of the load. And then in the spring and summer, when the snow melts and runs off, you're going to see the water loss. So that's the first thing. So that'll be each season. And then we're also measuring water change during the drought. So there was a drought from 3 years, from October 2006 to October 2009. So that'll be the first drought. Okay. Yeah. Okay, here's the movie. Here's the time each month. The blues show water gain. This is water change in total water relative to January 2011, which is about halfway through the sequence. And you can see in the fall and winter, the amount of water change in California's mountains, the amount of water increases, and you get a lot of blues, a lot of water gain, and then in the spring and summer, there's a lot of water decrease, you get a lot of reds. So what's coming up from October 2009 to April 2011, we have a big storms those 2 years, heavy precip, and you'll see all these blues coming up on the picture. So that'll be the 2 years from 2009 to 2011. Then we had, of course, 4 years of drought. And you'll just see them coming up. Here's the drought coming. The maximum is about in a year, October 2015. And this is the summer of the biggest drought. And you'll see all the reds indicating water loss throughout California's mountains, the Klamath Mountains, and parts of the western U.S. Sure. And it goes all the way through October 2017. That's last month. So turn to... Okay, how do we do this? Solid Earth's elastic response to a load is well known. If you put a disk of water on that's 1 meter thick and 14 kilometers in radius, you know nearly no Earth's response. It's about 2.7 millimeters right at the load center, and it decreases to about half a millimeter per year at the edge of the disk. We're finding Well, solid Earth's elastic response is not very sensitive to the rheology of the Earth, in particular for loads more than about 50 kilometers across. So we must distinguish between water in the mountains and its response, and water in the aquifers. The aquifers respond in the opposite fashion to a water increase than the mountains. When you put water on the mountains, they subside in elastic response to the weight of the load. When you put water in the aquifers, such as the Central Valley, the water fills up the sands, the pores in between the silt sands and gravels in the aquifers, so it expands and rises. So you're probably familiar with the substance of the Central Valley. That's because we're pumping out water. The pores in the gravels are contracting, and we get subsidence. So sure.
Just say next slide.
We're using GPS in your car. GPS is good to 10 or 20 meters. On my floor at JPL, we get the accuracy of GPS to about 3 millimeters in the vertical. Next. So we've developed a series of about 8 steps to get from the GPS vertical displacements to water series. One, we construct a GPS series of vertical displacements without any offsets. No offsets due to antenna substitutions or earthquakes. 2, we remove all the GPS sites in the aquifers. 3, we remove all the GPS sites influenced by volcanic activity. 4, we subtract from the GPS vertical displacements the weight of the elastic vertical displacements created by the weight of the atmosphere. 5 is the next slide. We also remove the elastic vertical displacement due to change in surface water in artificial reservoirs, which is known and reported by CDEC. We remove solid Earth's elastic response to unloading of the ice sheets 15 to 5,000 years ago. Next slide. And then we invert for change in water using that relationship with the bucket and the curve. We invert each month at a 1/4 degree lat law in pixels. We apply a regularization constraint to limit the amount of water change from one pixel to the next. And we assume we know what groundwater change in Central Valley is. We set it to equal to an a priori hydrology model, CVHM, because we can't get that from GPS. Next slide. So this part is on sustained changes in water during drought and heavy precip. Next slide. In California, we've had 3 years of drought, followed by 2 years of heavy precip, followed by 2012 should be drought, all the way to 2015, and then 2 years of heavy precip again. Next slide. During heavy precipitation from October 2009 to October 2011, the Earth's surface in California subsides between 5 millimeters and 12 millimeters. And we get an increase of water thickness, equivalent water thickness in California's mountains by 1/4 of a meter to 1/2 a meter. The water gain in the 4 provinces is about 30 cubic kilometers. Next slide. Okay, this is the big 4-year drought, severe drought. Earth's surface rose 10 to 24 millimeters in California's mountains. That's because we took the water off. We got up to 1 meter of water loss in the Sierra Nevada, the Klamath Mountains. and we lost a huge amount of water, 110 cubic kilometers of water. So in the next slide, I'm going to show you the comparison between our GPS results and the hydrology models. This is the hydrology model. There's the GPS. There's hardly any water change during the 4 years of drought in the hydrology models. The hydrology model consists of snow and soil moisture and NL-NOAA. So we're finding a big result from the GPS. There must be a bigger capacity for the mountains, for the earth to store water than in the hydrology models. And one thing I forgot to say, we go from October to October because there's no snow accumulation in October, so this all must be water in the ground. It's either deep soil moisture not in the hydrology models, or it's groundwater in alluvium adjacent to rivers, or groundwater in crystalline, in fractures in crystalline basement. Next slide. During the last 24 months, October 2015 to 2017, we had heavy rains and snow. California subsided 5 to 15, 18 millimeters. And then we've had an increase of water, more than 0.5 of a meter. In the 4 California provinces, we've had about 60 cubic kilometers of water gain. That's about half of what we lost during the drought. Next slide. Okay, these are the 4 mountain provinces we're measuring. Well, we're measuring it throughout the United States. These are the 4 I'm plotting: the Sierra Nevada, the Southern Cascades, the Klamath Mountains, and the California Coast Ranges. Next slide. So here's the movie again. This is the 4 California provinces. And maybe we could just enjoy for a while. The GPS is tracking the GRACE, or they're very similar. We're finding there's more water change from GPS than from GRACE, about 50% more, maybe nearly twice as much. So there's the water gain during the heavy precip. And now the drought is coming. The contours are at quarter-meter intervals. And here you can see that GPS is going to go a few months longer than GRACE. I think we got the last good GRACE results in June 2017, and we have the GPS through October. So the GPS can start to fill in for the gap before the GRACE follow on. Next slide, please. Oh, this is also providing insight into water cycle processes. This is water change in the Sierra Nevada from GPS. You can see the big drought and then the recovery. Here's the hydrology model. There's no big drought or recovery. So if we take the difference, we can infer what the change in water in the ground is. And that's this curve. So we have this big residual decrease. We can interpret the residual to be either deep soil moisture not in the hydrology model, or groundwater change in river alluvium or crystalline basement fracture not modeled in the hydrology model. And then each spring, we find that as the snow melts, the ground is being soaked with water. It's seeping into the ground. So we find big increases in water when when the water is seeping into the ground or infiltrating the ground. And then each summer, in the summer and continuing some years into the fall, we're finding parching of the ground, so the water is being removed from the ground. And this is not in the hydrology model, so we've got a real input from the GPS into the hydrology models. Next slide. Conclusions, next slide. Okay, we've used a new technique, GPS, to infer water storage across the western U.S. each month over 12 years. This is going to be a strong complement to GRACE. It's got the spatial resolution better, but we can't get groundwater change in aquifers. Next. I didn't talk about this very much, but from October 2011 to October 2015, we found the Sierra rose 24 millimeters from GPS. We're finding that Central Valley groundwater loss only accounts for 5 millimeters of that loss. Tectonic uplift can be 2 millimeters, and the remaining 17 millimeters must be water loss in the Sierra Nevada mountains itself. Next slide. Water changes are sustained over periods of drought or heavy precip. Next slide. So that's result 3. I've already said that a couple times.